Another technology we'll have a look at the ILabX is routing. Routing is a fundamental part of network communication. What you see here is the internet map of city-to-city communications. It might look like there's a direct communication between each partner. But on the way from sender to destination there are several so-called hops. Each of these hops needs to forward the messages he receives. To find the right next hop, routing is needed. Consider this easy example of sending a letter to your darling. What you have to do is write a letter, put an address on it, and bring it to a post box. From there on, the post will do the rest. What you have here are post offices that decide which way the letter has to take. They are routing your letter. And that's basically what happens inside a network when you communicate to a foreign host. Now, this is a network you will consider at the exercise. Imagine there's a new network joining. In this case, network 3 and router 3 join the network. Like in the former example, we have a couple that wants to communicate. In this case, host 1 and host 5. What will happen is that host 1 sends the message to router 1, which is his entry point to the network. Since router 1 does not know a route to network 3, it will answer with an error message. To solve the problem, we'll have a closer look at what happens inside a router. Your PC packs tiny little data packets, labels them with the address information of your destination, and hands them over to the router. The router now decides upon his list of routes to different locations where to send the packet. There are two actions that have to be performed. The first action is the routing. This is the process of finding an adequate route to the destination. The following retransmission to the chosen hop is then called the forwarding. In huge-sized networks, like the internet, there will be several routers or hops on the path to your destination. Here you can see the slightly simplified routing table of router 1. When router 1 receives a packet with destination host 5, he takes the IP address of the packet's destination and does a lookup for the corresponding subnet prefix in his routing table. Here this is marked purple. In his table he finds an entry which says that the next hop is the green address. This is the IPv6 address of router 3. So router 1 forwards the packet to router 3. Router 3 will then do the same again, and he will see that host 5 is directly connected. So finally the packet will be delivered to host 5. If you now remember the example from the beginning, we had the issue that there was no route to a destination. So how do routers get their destination routes? On the one hand, they can be manually configured. In modern networks with lots of routers, this is no option. What is used instead are dynamic routing protocols like OSPF, RIP, BGP, just to name a few of them. In the lab, we will have a deeper look at them and their underlying principles. Thanks for watching and see you at the ILabX. What you can see here is an instance of a virtual lab environment. You have our local network 1, local network 2 and the server zone who are configured and can talk to each other. And you have the fourth network, local network 3, which is joining this network. So what we'll try now is that we try to ping from host 1 to host 5. First I have to start the lab environment and have to wait till all of these boxes are green. That means till all of these hosts are up. Now I can start a shell at host 1 and try to ping host 5, which is ping -6 and the IP address of host 5. If we do so, we receive this error message, destination unreachable, no route. This means our packet gets stuck somewhere here in the network. To see where it gets stuck, we can use traceroute -6 and again the IP address of host 5. And we'll see the first hop of our packet is router 1, and the second hop is router 2. So this means our packet gets stuck somewhere here at router 2. And if we try to use Wireshark on ETH1, which is this interface, and try to ping again, we can also see this packet is received by router 2 and gets answered by this ICMP error message. And if we have a look at this ICMP error message, we also see that this is the source address and this is the address of router 2. So as it says no route to destination, we can have a closer look at the routing table of router 2. We can do so by opening a new shell and entering IP-6 root, which shows the routing table of router 2. If we now compare it with our IPv6 address of host 5, we'll see, okay, we have an entry for 2001, DB8, BE11, 22, 33, but no for 44, like it's on our IPv6 address of host 5. So, as it says, there's no route to host 5. What we can do now is we can either manually configure this route and say, okay, router 5 goes via router 3, or we can start a dynamic routing protocol on each of these routers. So what we can do, for example, is we start OSPF by entering the command OSPF6D on each of these routers. So we have router 2, we have router 1, OSPF6D, and we have router 3, OSPF6D, and now we ping again. And we see we get the same error message, destination unreachable, no route. But if we wait till all of these routers exchange their routing information, we should get a route. So it can take some time, maybe 30 seconds, around 30 seconds, till these messages are exchanged. And then we should see here our route. So as you can see here, there's some action going on. And now you see the ping gets through and we have host 5 answering. So if we now again use traceroute, you can see here router 1, router 3 and host 5. So what also happened is router 1 gets the shorter route to host 5, not via router 2, but via router 3. So our packet travels from host 1 to router 3 to host 5. And if we now have a look again at the routing table of router 2, for example, IP-6 route, we see here is now the entry for 2001 DB8 BE44. So now the routers exchange their routing tables dynamically, and we can communicate from host 1 to host 5.